All right, pre-calc, we're back for part 2 of section 1.5. This is the first lesson there. Pretty much where we left off at this sort of like as our base for all logic when we're talking about complex expressions. So trying another one where we've got I to the 73 power. I guess my simplest approach was to take any odd power and just say, hey, it's I times I to the 72. And maybe, if I wasn't clear on that first video, I'm assuming that, hey, I is to the first power, so 1 plus 72 is 73. But I think you guys understand that. So at this point, you guys can just say, hey, it's I times I squared, and then you just take 72 divided by 2 to figure out what that power should be, to the 36th power. So I squared is always negative 1. You're taking negative 1 to an even power, thereby making it I times positive 1. So yeah, it's just I, or 1I. For number 17 in the textbook. Part B is pretty similar. I could also rewrite this as 1 over I to the 46th power. That's another way to think about it right away, as negative exponents belong in the bottom parts of fractions if there's no fraction specified. It's even, so I'm not going to say I times a new power because it's going to be I squared to the 46 divided by 2, 23rd power. It's a negative 1 inside here to a 23rd power. Negative 1 to an odd power is negative 1. So 1 over negative 1 is negative 1. So hopefully you guys got a good feel for that. 23. Very different problem. The idea is we want to write it in this format, A plus BI. But we're never going to get that done with this fraction in play. So we have to figure out a way to eliminate this fraction, at bare minimum, make the bottom how should we put this? We need to make this function a rational bottom value of a integer. Yeah. Sorry, I was kind of clunky with that explanation. Basically, we need to be, this bottom number needs to be I-less. No i's on the bottom of this fraction. So what are we supposed to do? Well, I think you guys remember seeing how to rationalize functions that look kind of like this. Say you had 1 over 1 minus root 2. I know you guys have seen this before because it was a big thing in Math 3. If you wanted to create a fraction without roots at the bottom, the idea was if I could essentially square out this root 2, I'd be okay. And you can do that. You can do that with differences of perfect squares. We talked about that in factoring earlier this year. Bottom line is if you multiply by the opposite of what you see here, you create a difference of perfect squares. It's actually called the conjugate, okay? Multiplying the bottom, really any term by the conjugate, creates this. 1 times 1, 1 times positive root 2, negative root 2 times positive 1, and negative root 2 times positive root 2. So that would be negative root 2 times root 2. That's just going to be 2. You make those middle roots cancel. In this case, leaving the bottom to be negative 1. That's what we want to do over there. We want to create a difference of perfect squares so that all we really need to do is square the first and then square the last. Because if we can do that here, you're squaring an I term, which would be negative 1, and you'd be squaring a 2 here. So we multiply by the conjugate. I'd write that down in your notes. Multiply by the conjugate. right, so I've eliminated the workspace there, so let me re-establish my territory. Okay, so the conjugate, we're mostly concerned with the bottom part of the fraction, making the bottom part of the fraction have no i's in it. So you multiply by 2 minus 7i. You got to do it to the top as well. So here's the deal. The shortcut has been established when it's a difference of perfect squares. All you got to do is say, square the first. That'll give you 2 times 2, 4. Square the last, it would give you negative 49i squared. And then you just work out the top. Negative 4 times 2, I'm just going to do a little scratch work over here. Negative 4 times 2 is negative 8. Ooh, that's a sad looking 8. Negative 4 times negative 7i is plus 28i. 6i times 2 is plus 12i. And then 6i times negative 7i is negative 42i squared. Now we can simplify this in 2 ways. The I squared is just negative 1. And this is 40i. So what is negative 42 times negative 1? Well, it's positive 42. So you're taking a positive 42 here and subtracting an 8. What you get is 34 plus 40i. On the bottom, this I squared can be removed and replaced with a negative 1, which means we're talking about 4 plus 49 in the denominator. That's 53 in the denominator. And there we go. We're pretty much there. It says to write it in terms of a plus bi. So technically I would have to split this up and call it 34 over 53 plus 40 over 53i. Yeah. Let me double check the answer on that. We're good. Let's try that again with 25. By the way, what I just erased right there, have that basically committed to memory. I mean, I think you can generate it from scratch every single time, but it just makes it easier to have the basics memorized. Oh, this one's a little different. It's only got one term on the bottom, 4 minus 2i over negative 7i. So it seems like maybe I just do something with the top because it seems to have a conjugate. But keep this in mind. You're trying to create a plus bi. A plus bi. I just need to make the bottom not an I term. So to get rid of the I term, I could just multiply by I because it would create I squared. I squared equals not an I term, negative 1. Boom. So make sure you do that on both the top and the bottom. You multiply the bottom by I. You got to multiply the top by I. The top looks like 4i minus 2i squared. The bottom looks like negative 7i squared. All right, so drink that in. That makes sense? I didn't have to multiply I didn't have to multiply by the conjugate. The I squared turns into a negative 1, and now we have that same thing that we desired on the other equation. We desired this 53, or some constant value like that. that didn't have an I in it. All right, I think I've made my point. So 4I minus 2 times negative 1 is 4I plus 2 over 7. Yeah, and to rewrite it in terms of A plus BI, I would say that this is 2/7 plus 4 over 7I. '27's different. And we're not going to do that one. We're doing 29. We're not given any expressions at the beginning with I's in it. We have to compute them ourselves. Don't be too terrified. Root negative 4 is the same as 2 times negative root I. I'm sorry, I totally butchered that. Root negative 4 equals 2 times root negative 1, which is I. All right, 2I. This is 2I. That is 2I. This minus, still there. So root negative 16 is the same example we had. It's 4I. All right, that looks very similar to what we had before. Go to town. Multiply it out. Negative times a negative is a positive. You know, when I worked through this in high school, I got into a habit of every time I saw an I squared, I just instantly changed the sign in front of its coefficient and dropped the I squared. Okay? I would say, you know, if you feel pretty confident about this, do the same thing. Those shortcuts are going to be really helpful in the long run because, you know, writing plus 8I squared versus just writing minus 8 is not that big of a deal when I'm checking work in my book. So you got 6 minus 8 is negative 2, negative 8 minus 6 is minus 14I. So feel free to employ that shortcut if you'd like. If not, you can go at it the long way where there's like maybe one extra step of rewriting it with the I squared as negative 1. Last example, number 31. Oh, it mixes the two concepts together. We got a top and a bottom in which no roots are simplified yet as i's. So let's get to it. All right, what do we got? All right, so the first thing you should do is change these radicals into some kind of I term, some type of complex expression. So the square root of 81 is 9. The negative root requires an I to replace it. So this will be 2 minus 3I. Now multiply by the conjugate of the bottom, because we want to make the bottom a non-I term. So here's the conjugate. 2 plus 3i, 2 plus 3i, both top and bottom. So make sure you put the grouping symbols everywhere they belong. The shortcut on the bottom is that you square the first, you square the last, and you put a minus in between them. However, instead of maybe the I squared, we just say, since that's -1, it's going to change the sign of this to plus, and then we can just say, all right, you've done your job, now go away. Save some space, right? So then you got 4 times 2 is 8. 4 times 3i is 12i. 9i times 2 is plus 18i. And then 9i times 3i is 27i squared. Or I can say it's a -27. Gone. So then 8 minus 27 should be -19. Plus 30i over 13. Final answer? -19/13 plus 30 over 13i. Not a really nice, neat solution, you know? All right, it checks out with the book. So I think you guys are ready. Hopefully this video was helpful. Thank you for watching, and stay tuned for more videos tomorrow on complex expressions.